Hello everybody and welcome to a new block of video lectures. Now we're going to start talking about models. Why? Well, because they form the basis for oral analysis. Everything we do, whether we are trying to better understand our object of study, or whether we want to test a specific hypothesis or make predictions, everything is one way or another based on a model of how reality works. And there are going to be many different concepts in these videos, such as reducible versus irreducible error, or bias and variance, overfitting, underfitting, cross-validation, a very long etc. We will see that the process of building a model is really all about trade-offs. A trade-off between how accurate the model is and how useful it is for our purpose, between how well it fits our data and how well it will generalize to other data, or how easy it is to interpret. Everything is about how useful the model is for us, for our purpose. And depending on what we build the model for, that is going to mean quite different things. Let's see. So if we take a look at the course again, we're going to move away from this part in which we had everything about the design. And we're going to start talking about this part, about actual analysis. And specifically in this lecture, we're going to talk about modeling and everything ultimately for the purpose of learning something new about our object of study. So let's see. This block is going to be about, first of all, introducing the difference between supervised and unsupervised learning. And then we're going to talk about how we specify a model, supervised or unsupervised, how we estimate the model, how we select among multiple models based on different criteria. And we're going to see different caveats of model selection, things that we have to consider when choosing one model or another. And everything is related to a very important concept in modeling, which is the bias variance trade-off. In the end, we're going to see that in practice, there are situations in which it's kind of nearly impossible to know really whether a model is good or not. And we have to kind of get around the certain limitations. And one way of doing that is cross-validation. Now we're going to get a little bit more technical, and let me just introduce a little bit of notation here, although you might be already familiar to it. When we see a capital X like this, that means a random variable that follows a certain distribution. And then a particular observation of that random variable is going to be denoted with a lowercase x. So when we refer to the expected value or the mean of that random variable given that distribution, we're going to write it like this, the expectation of x. We might also be interested in the variability in the random variable. So the variance, for example, that's going to be denoted var of x. And then when we want to estimate that value x given some data, some sample of data, if we want to guess or approximate under a certain uncertainty because we only have a sample, we don't have the full population, then we're going to use the hat on top of it. That's going to mean an estimation for x. And then whenever we see a bar over it, we know that it refers to the sample mean. So if we have, say, n random variables, x1 to xn, then if we compute the mean of those, that would be the sample mean. So that would be x bar. So when we talk about models, we really talk about statistical learning. And it's kind of the intersection between statistics and computer science, although there are very small nuances in there. It's about modeling complex data sets, about building models around complex data. Why do we build a model? Usually it's because of one of two things. Either we want to understand whatever phenomenon the data refers to, our object of study, or we want to use that data in order to build a model such that we can make predictions about that object of study. We're going to see that depending on whether we want to understand or to just make predictions, the techniques we use are quite different. And we typically classify these statistical learning techniques in two categories. It's either supervised or unsupervised learning. In supervised learning, what we do is estimate an output, a dependent variable, given some inputs or independent variables. And in unsupervised learning, we really don't have one variable that we can refer to as the dependent one. We only have observations of multiple variables, multiple independent variables. And what we want to do, what we're after, is try to find some underlying structure in the data such that we can use that structure for something, such as plotting data or simplifying learning models. Let's say we're interested in modeling the wage of employees as a function of their age. So salary as a function of age. Now, we know there's too much unexplained variability. If we look at the plot, here we have a scatter plot. Over the x-axis, we have the age. Over the y-axis, we have the wage. Every gray point here is an employee, and we see that there is a lot of variability. So even if we try and fit a good model, let's say this blue line over here tries to model the relationship between wage and age, we see that there is still a lot of variability. There is a lot of error in those models. And so there's too much unexplained variability in the response, in the wage, even after trying to model it using the age. So age alone is not going to be enough to have a good model of the wage. What else can we try? Well, we could try different models, but regardless of what we try, there's just too much variation. So we should try and look for additional variables. One of those variables could be the year that the data refers to. So if we plot again here the data by year, we see that there seems to be a slight increase. There's a positive correlation between wage and year. Sure, there's still a huge amount of variability, but we could try and leverage the information about the year to come up with a better model. Still, it's nowhere near enough, but it's going to be a little bit more helpful. And you might think, why do we add the year? Well, because hopefully the salaries increase every year. We can think about inflation and that kind of thing. So it makes sense that we include this as a predictor of the wage. What else can we do? We could think, for example, about the level of education. So over here, we have box plots for the wage given the level of education of the employee, anywhere between primary school to PhD. And we see that, yes, thankfully, the more you study, then the higher your salary. But still, there is a lot of variation. We could maybe come up with a decent model based on the age, the year, and the education, try to leverage these three independent variables to try and predict or understand how they influence the wage of an employee. So this case is an example of what we call supervised learning, because there is a dependent variable, the wage, and we want to model it as a function of three independent variables, namely the age, the year, and the level of education. More generally, we have a dependent variable y, and we want to build a model of y as a function of p independent variables, x1 to xp. So it's all about finding this function, this model about predicting y depending on these p x's. And typically, depending on the form of y, we talk about regression or classification. If the response y is numerical, then we have a regression problem. If the response is nominal or categorical, then we have a classification problem. Let's see some examples. Now, again, we're trying to model the salary, which is a numerical variable, as a function of age and level of education. This is a regression problem. Let's say we want to model the water level based on the weather forecast. So the weather forecast would be the x's, x1 to xp, and we're trying to model the water level, which is the y. Let's say it's numerical, and therefore this is a regression problem. What are examples of classification problems? It could be, for example, whether we should accept or reject an application based on a banking profile. Say someone is applying for a mortgage, and we have data about whether we should accept or reject based on certain risk indicators given the banking profile of a person. This would be the x1 to xp's, and this would be the y. There's no 0, 1, 2, 3. There's no numerical response here. It's just categorical, either accept or reject. Or let's say that we're trying to predict, based on the socioeconomic index of people, whether they are more likely to take the bus, the tram, the bike, the car, etc. This would be the dependent variable. It's categorical because there's no order, for example, between bus and tram. And then we have unsupervised learning. And the thing here is that we have, again, p observed variables, but there is no concept of dependent variable, or at least it doesn't make sense to say that one of them should be modeled as a function of the others. And what we're trying to find here is some unobserved latent variables, z1 to zq, whatever q number is. And the point is that we have certain structure underlying our data. We don't observe it, but we hypothesize there is such structure. And what we try to do is find that structure. So it's something in the lines of trying to find these Z variables such that, given a certain model of them, those are the ones that kind of generate this data, or the ones upon which the actual observations depend on. And so here again, we normally divide into classes of models, those that are targeted at clustering or dimensionality reduction. In clustering, what we want to find is some latent structure in the form of a categorical or nominal variable. So let's say that we have data about cities, and what we want to do is group the cities, come up with groups or clusters of cities based on how they use their land and social economic activity. So let's say the X's are variables that have to do with land use and economic activity. And then we want to group cities based on how similar they are with respect to those observations. Or let's say that we have data about different discrimination factors in a department in a company, and what we want to do is try to group departments according to how similar they are with respect to those discrimination factors. And then dimensionality reduction is about simplifying complex data sets such that we come up with reduced data sets that are easier to work with, and still we retain most of the information in the original data. So let's say we have a data set with 1,000 different variables, and we want to reduce just to maybe 2 or 3 or 20, and still retain most of the information we have in the 1,000 variables. Why? Well, because it's a lot easier to work with just 10 variables rather than 1,000 variables. Perhaps it's easier if we illustrate a little bit more. So let's say we have our typical table of data. Over the rows we have observations, and we have x1 to xp variables. These are the observations we have. Now, if we do have the notion of a certain y, and we want to model how y is affected by this x1 to xp, then this is a supervised learning problem. And then depending on whether y is numerical or categorical, then we have regression or classification. And if we don't have this notion of dependent variable, no notion of the y, then we just have this x1 to xp. And what we want to find is some other variables that are latent in the sense that we don't observe them, but we hypothesize that they are. And then we have z1 to zq. And in this case, this would be dimensionality reduction. If we typically here we talk about numerical variables. If what we want to find is just this one variable z, and it's categorical, and what it's going to do is just organize all these observations into different groups or different clusters, and this is called clustering. So supervised learning is going to be very handy when we are in situations in which collecting data is easy or cheap. Collecting the x's, it's easy, but collecting the y's is not. So for example, if we have a data set about, I don't know, animals, and we want to classify whether the picture we're seeing is of a cat or a dog or an elephant or whatever, coming up with those labels is going to be hard, because then we have to ask people whether this is a cat or an elephant or a giraffe or a lion or whatever it is. But if we have tons and tons of data, which are easy to gather nowadays, we can have more and more and more and more pictures. We might just try to come up with those labels of the animals by trying to cluster all those pictures together by different variables about the picture, such as the color, the shapes, etc. And so trying to ask persons whether this is an animal or another animal, it's going to be expensive. But just throwing all the data to a certain algorithm to try and find those clusters itself might be enough. Of course, it's going to be noisy because it's not going to be perfect. Sometimes it's going to give us a label that doesn't work out, but it's going to be enough in some situations. And of course, it will not tell us this is a cat or this is a dog. It will just say, these pictures seem to be about the same animal. Whatever that is, I have no idea what it is. I'm just going to call it cluster 1 or cluster 2. And then you figure it out. And so if we're trying to, for example, build a very complex model to recognize animals, that model surely is going to need a lot of data. And one way to provide data to that model, maybe noisy data, is to use clustering. So in the following videos, we're going to see everything about choosing one family of models or another, how we specify the models, how we measure how good they are, different caveats in choosing one model or another, and in the end, many trade-offs we have to think about.